Hello everyone. Welcome to joining us in the low temperature thermochronology online lectures. Today, we'll be learning Chapter 3. I'm Nitao from School of Earth Science and Resources, Chang'an University. Chapter 3 will learn the uranium, thorium, helium thermochronology theory background, and we'll be going through Section 4. Section 4 is about partial retention zone. Helium is progressively lost by diffusion as temperature increases. Helium thermochronology is based upon the accumulation of helium-4 in rocks and minerals over geological time due to the radioactive decay of naturally occurring uranium, thorium, and samarium. Although helium-4 is being produced by the decay, when the rocks are hot, the helium-4 will not be retained in the crystals and will instead diffuse out of the system and into the atmosphere, where it makes up about 1 ppm or 0.001% of what we breathe. Thermochronometric partial retention zones, or fossil partial retention zones, are often identified quantitatively in geological studies as a characteristic distribution of apparent dates with depth or elevation. The helium partial retention zone of each thermochronometer is defined by upper and lower boundaries, indicating 90% and 10% retention respectively after being held at a steady temperature for a specific amount of time. Apatite helium partial retention zone reflects temperature range over which 10 to 90% of the helium is retained in apatite. For slow-cooled sample, helium partial retention zone is more relevant than closure temperature. Helium partial retention zone extends from about 40 degrees centigrade to 85 degrees at the Earth's surface and at depths corresponding to temperatures below 40 degrees. Helium is quantitatively retained and helium ages track calendar time. While at temperatures higher than 80 degrees, helium is lost as rapidly as it is produced, so helium ages remain essentially zero. Helium partial retention zone is a temperature-sensitive region between these two limits, where helium age increases with calendar time, but with a less level due to helium diffusion. After a sufficiently long period, a balance between helium ingrowth and diffusion loss will be established. Meanwhile, a steady-state helium age will be achieved. This steady state will be achieved at higher temperatures first. So while ages at depth become invariant, those at shallow depths continue to increase. This figure here illustrates partial retention zone. As we can see that this shaded zone shows partial retention zone, and above it, as temperature goes higher, is the total diffusion zone where helium will be totally diffused. And at lower temperatures is the total retention zone, where no helium will be diffused. In other words, all of the helium products will be retained. Laboratory experiments on thermal-activated three-dimensional helium diffusion give this relationship between diffusivity and temperature, where D is the diffusivity, DO is the diffusivity at infinite high temperatures, EA is the activation energy, and R is the gas constant, T is the temperature, and A is the diffusion domain radius. It is important to see that in this figure, the straight line defines volume diffusion, where the slope is activation energy, which the intercept is diffusion rate. Helium derived from alpha decay and uranium and thorium series keep molecular motion. Industrial products could never be absolutely isolated from the outer environment ever since its ingrowth. In fact, Helium interacts with the surrounding through different forms. Alpha ejection is a case in point. The other key mechanism is diffusion, as we can see in the figure on the left. The present-day helium constant is basically the outcome of competing effects of alpha ingrowth plus alpha ejection process and alpha diffuse. The diffusion of helium with the metric mass is widely spread in terms of both phase and temperature. Helium diffusion from a variety of apatites including Durango apatite, a common apatite standard obeys the relationship, suggesting that helium diffusion from apatite is a single mechanism, thermally activated volume diffusion process, at least at temperatures below 300 degrees centigrade. Limited high-quality diffusion data indicate apatite helium closure temperature is about 70 degrees, with a cooling rate at 10 degrees per million years. This is so far the lowest known closure temperature among radiometric dating techniques. And the closure temperature for zircon is about 180 degrees when the radiation damage is below a certain level. Variation of closure temperature with grain size and cooling rate is shown in this figure. The closure temperature of helium system depends on a variety of factors, including the cooling rate, crystal size, and what minerals you are interested in as well. For example, helium-4 is typically only retained in apatite when the crystal cools below about 70 degrees centigrade, and in undamaged zircons when it cools below about 180 degrees. Because the Earth gets hotter as you go deeper, the cooling history of a rock often tracks its path from the deep Earth up to the surface. The above is all about the partial retention zone. Thank you.